Welcome back, everyone, to part 2 of our software engineering course. I am absolutely thrilled to kick off this next major phase of our journey together. Up until now, we've talked a lot about gathering requirements, agile development, and designing system architecture. But today, we're shifting gears to something that is arguably the absolute most critical aspect of modern software engineering, and that is dependable systems. We're going to look at what it truly takes to build software that people, businesses, and society as a whole can actually trust.
Here is our roadmap for today's explainer. We're going to start with an introduction to dependability, move right on to the socio-technical perspective, break down the 5 dimensions of dependability, examine the cost of dependability, and then wrap it all up with a summary and exam focus to help you structure your note-taking.
All right, let's jump right in with Section 1, Introduction to Dependability.
Before we get bogged down in formal definitions, I want you to ponder a core question. Why might trusting a system actually be more important than its detailed functionality? Keep that in the back of your mind. Formally, dependability is a property of a system that reflects its trustworthiness and the degree of confidence a user has that it's going to operate exactly as expected. This specific term was actually proposed by a researcher named Jean-Claude Laprie back in 1995 and then refined in 2004 to serve as an umbrella term. So rather than just saying a system is bug-free, dependability covers several linked attributes that dictate whether we can truly rely on it. It's not just some numerical value, it's really all about user confidence.
So, getting back to my earlier question, why does this matter more than having, say, 100 flashy features? Well, first off, system failures affect massive numbers of users. Think about it. If a rarely used feature is left out, only a few people really care. But if the entire system goes down, normal business literally grinds to a halt. Second, users will outright reject unreliable, unsafe, or insecure systems. If a user doesn't trust your application to keep their private data safe, they're going to take their business elsewhere, completely regardless of how pretty your user interface is. Third, system failure costs are absolutely enormous. We're talking about things that can sometimes bankrupt entire companies. And finally, undependable systems cause expensive data loss, which is incredibly difficult and costly to recover. Moving right along, let's look at Section 2, the socio-technical perspective. Now, this perspective shatters a very common student misconception, the idea that software just exists in a vacuum. You see, as software engineers, it is so easy to think we only need to worry about writing isolated code, but software is actually part of what we call a socio-technical system. This is a holistic system that includes the hardware the code runs on, the software itself, and the human operators, all situated within a specific organizational environment. You simply cannot design dependable software without considering the physical hardware it sits on and the actual human beings who are going to use it. This holistic view is necessary because system failures come from a variety of sources. Your system hardware might fail because of manufacturing errors or even environmental factors like the server room overheating. System software might fail because of bugs or mistakes made during the specification phase. And then operational failure occurs when human users fail to use the system as intended. The absolutely crucial point here is that these are all interconnected. A hardware glitch might cause an unexpected system state, putting a human operator under severe stress. Stressed people make operational mistakes, which might feed incorrect inputs back into the software, causing a total system crash. It is a catastrophic chain reaction. So, to quickly recap before we move into our core framework, software operates in a socio-technical environment. If you want to achieve true dependability, you absolutely must address hardware, software, and human factors holistically. Remember, you are designing for the messy real world, not just for a compiler.
Okay, let's dive into Section 3, the 5 dimensions of dependability.
This is the central framework of our explainer today, detailing the specific properties that make up a dependable system. The first dimension is availability. Simply put, this is the probability that a system will be up and running and able to deliver useful services to users at any given time. Basically, is the system actually there when you ask for it? For something like a bank's ATM network, availability is often the absolute highest priority. The second dimension is reliability. This is the probability over a given period of time that the system will correctly deliver services exactly as expected by the user. Now, it's really important to distinguish this from availability. Availability just asks, is it running? Reliability goes a step further and asks, is it producing the correct behavior and results consistently over time? Next up, we have safety. This is a judgment of how likely it is that the system will operate without causing catastrophic damage or injury to people or the environment. When we talk about flight control software in a passenger aircraft or the software running a massive chemical plant, safety is paramount. The system must fail safely without causing human lives. Our fourth dimension is security. This is a judgment of how likely it is that the system can protect itself against deliberate or accidental unauthorized intrusions. Security ensures that malicious attackers, or honestly, even accidental internal errors, cannot compromise the system's data or integrity.
Finally, the fifth dimension is resilience. This is actually a newer addition to Lapri's original model. It is a judgment of how well a system can maintain the continuity of its critical services in the presence of disruptive events. If a cyber attack actually succeeds or a major equipment failure happens, can the system recover and maintain its most critical services? That is resilience. Now let's ground these abstract concepts with a few practical engineering scenarios straight from the textbook. Look at the insulin pump. It's a life-saving medical device. Therefore, reliability and safety are its most critical properties. It must reliably deliver the exact correct dose of insulin, and it must safely ensure it never delivers a lethal overdose. Next, consider the wilderness weather station. Because it's placed out in a remote environment where sending a technician is wildly expensive, availability and reliability are key. You just can't easily go fix it if it breaks. Finally, we have MedCare, a patient information system. Because it holds highly sensitive medical records, security is the top priority, to protect that data alongside resilience to ensure patient consultations aren't interrupted by sudden system faults. The big takeaway here, not every system prioritizes all 5 dimensions equally. It entirely depends on the context.
So how do we actually build these highly dependable systems? Well, here are 4 sequential steps for dependable software. Step 1, avoid introducing accidental errors during your specification and development phases. Step 2, design rigorous verification and validation processes to find any residual errors you might have missed. Step 3, design for fault tolerance, meaning the system can just keep on working even when a fault does occur. And step 4, design protection mechanisms that actively guard against external attacks. Basically, avoid, find, tolerate, and protect.
Now let's talk economics in Section 4, the cost of dependability. I want to pose a slightly provocative question to challenge you on the practical realities of engineering. Why is it impossible to achieve 100% dependability for free? We all want perfect software, right? But in the real world of software engineering, perfection comes at a very, very steep price. The reality of the cost and dependability curve is quite stark. Achieving basic dependability is relatively low cost. If you use standard, good software engineering practices, you can get a decently dependable system fairly cheaply. But look at what happens when you try to reach ultra-high dependability for things like aircraft navigation or safety-critical medical devices. The cost and the time required experience an exponential spike. Why? Because of the massive amount of verification, validation, and exhaustive testing required to prove, often to very strict external regulators, that the system will virtually never fail. To recap this vital economic concept, achieving basic dependability is relatively cheap, but reaching ultra-high dependability incurs exponential testing and validation costs. As an engineer, you must always balance the level of dependability required by the system against the economic realities of your project budget. All right, let's bring it all together in Section 5, Summary and Exam Focus. I want to make absolutely sure you are fully prepared for when these topics come up in your assessments. Here is exactly what you need to memorize. First, you must be able to explain why dependability is often considered way more critical than detailed functionality. Remember to mention the huge costs of system failure and user rejection. Second, you must be able to list and formally define the 5 principal dimensions: availability, reliability, safety, security, and resilience. Third, you absolutely must understand the holistic socio-technical view. Do not write on your test that software engineers only care about code. You must emphasize hardware, software, and humans. And lastly, know how to explain that exponential cost curve for ultra-dependable systems. Up next in our course, we're going to transition into reliability engineering. We will take all these foundational theories we learned today and see how fault-tolerant architectures and advanced testing put them into actual rigorous practice. I'll leave you with this final provocative thought. If an ultra-dependable billion-dollar software system fails completely just because a stressed, untrained human operator made a typo, was the system ever truly dependable in the first place? Remember, it's all interconnected. Thank you so much for joining me, and I will see you in the next explainer.